Good morning, good afternoon, good evening to everyone joining the webinar today. Um, my name is Oliver Greaveson, and I'm going to be hosting today's webinar on delivering digital water global case studies. We've got some fantastic case studies from around the world that I'll wait till everyone coming in. Thank you, Erin. So a bit of an agenda today. I'm going to do a bit of an introduction. As I said, my name's Oliver Greaveson. I'm an Associate Director at the engineering consultancy Atkins Realis, as well as the chair of the IWA Digital Water Programme. We're going to see two fantastic case studies from around the world. Firstly, we're going to see Yu Feng from Three Gorges Water, Smart Water Technology, looking at developing digital twins of the wastewater system. And then secondly, we're going to see Marina from Brazil, looking at digital water and resilience and a case study from Brazil. Both Yufeng and Marina are members of the IWA Digital Water Programme, and really fantastic case studies. At the end of today, we'll have a bit of a Q&A panel discussion. We've got about 20-25 minutes, and I'll close at the end of that. It's going to take roughly an hour to an hour and a half in total. So, Erin, next. This webinar will be recorded and made available on demand on IWA Connect Plus platform and the IWA Network website with presentation slides and other information. The speakers are responsible for securing the copyright permissions for any of the work that they will present, of which they are not the legal copyright holder. The opinions, hypotheses, conclusions, or recommendations contained in the presentations and other materials are the sole responsibility of the speakers and, of course, me, and do not necessarily reflect the IWA opinion. That's something I am legally obliged to read out. So, in terms of the webinar information, there is a chat box. Please use this for general requests and for interactive activities. If you've got a question, I will look at it but only if it's in the Q&A box. Please use this to send questions to the panelists, and we'll answer these questions during the discussions. We will potentially answer them online as well as we go through from the speakers. Your microphones are muted. We can't respond to raised hands, so either put it in the chat box or in the Q&A box if it's an actual question about the subject matter. So, Digital Water Programme, if you are not aware, the IWA has a Digital Water Programme. It aims to act as a catalyst for innovation, knowledge and best practice around digitalisation for the water industry, provide a platform to share experience and promote leadership in transitioning to digital water solutions. There is lots and lots of material on there, some brilliant white papers and more coming out. We'll soon have the resilience white paper coming out. And of course, there is the Digital Water Summit next week. So do sign up for that if you're not already. The programme is driven by the end users, utilities, regulators, and also the solution providers out there. Digital water is still emerging in the industry, and we still need the vital part of today is all about bringing the case studies and seeing what we've done on a global basis and seeing how we can use that to solve the urgent problems that we've got in the industry. We've all seen pollution, we've all seen climate change happen. Digital water is a part of that solution. The overall goal of the programme is to facilitate utilities access to knowledge that enhances the rate of succession, enhances us being able to adopt digital transformation. The objective of the programme ensure this goal can be achieved. So it's really important. It's all led by the Digital Water Programme Steering Committee, a wonderful group who helped me go through, develop the content. We're always looking for content, always looking for people willing to lead in digital water. They're all there. It's all on the website. The 2023-25 Steering Committee was recently announced with a 55% female and 50% representing low and middle income countries. Digital water is global. It's everyone is affected by it. So that's the Digital Water Programme Steering Committee. The goal, thank you, Erin, is to facilitate embedding digital at the core of the water profession. we're seeing more and more and more data. My own area of wastewater, I think in England alone, we're going to be seeing in the next 10 years 56,000 regulatory monitors across England, which, face it, is a relatively small country. The objectives of collating knowledge and insights from members, empowering members and empowering utilities around the world. There's lots of webinars, blogs, videos. This obviously, this webinar today, lots of great things, and of course, the Digital Water Summit next week. The next, Erin. As I said earlier, lots of publications, podcasts, meetings out there. Do go on to the Digital Water Programme website on the IWA website or in IWA Connect. There is huge amounts there to get involved in, and of course webinars like we have today. So who have we got today? We've got me, and I'm very quickly going to hand over to Yufeng in a second. And Yufeng is going to host our first demonstration, our first case study, and Marina is going to host our second. So I'll give you a brief introduction to Yufeng before we hand over, and in between I'll introduce Marina. So Yufeng is currently the Vice General Manager of Three Gorges Smart Water Technologies Company. He holds a PhD in hydroinformatics from the University of Exeter and holds positions as a member of the IWA Digital Water Programme Steering Committee and co-chairman of the China subgroup, who do some amazing work, and a member of the Smart Water Steering Committee of the China Urban Water Association. Yufeng's been working, has a career spanning 20 years in water management. He was a technical director of water and environment at Atkins in China, the operations director of municipal water at Veolia in China, and the deputy general manager at HR Wallingford in China. He's got a huge and extensive experience in water engineering, planning, design, operation, and consulting, with a specialization in digital water, numerical modeling, and urban flood management. So at that, I'm going to hand over to Yufeng. Next, Erin. He's going to talk to us about developing digital twins of the wastewater system, which, to be fair, I've been waiting to see for the past 10 years. So I'm really looking forward to this one. Yufeng, do you want to take over?
Okay, thank you. Thanks a lot, Oliver. Hello, everyone. This is Yufeng from Three Gorges Smart Water Technology. And today I'm going to introduce a case study of digital water transformation in China. My presentation will include 4 parts. First, I will give a brief introduction of the project background, then the framework and the methodology we applied for this project. The third, I will give some details, present some details of the digital twins in Zhejiang City, basically the project where it's located. Finally, I will give a brief summary on the achievements of the projects. Gorges Smart Water Technology. It's a subsidiary of state-owned company China Three Gorges Group. We have 2 offices currently in China, one in Shanghai, one in Wuhan. If you, any of you come to China, to Shanghai or Wuhan city, feel very free to contact with us. We are recently funded only in 2021. Currently, we have around 150 staff. We currently have 8 business areas associated with digital water. It's including design and consulting, data management, software and platform development, monitoring schemes, numerical modeling, digital system deployment and maintenance, and associated research and development. Now I moved to the project I'm going to present today. Zhejiang project is actually under a bigger project called Great Protection of the Yangtze River. Yangtze River is the largest river in China with diversity, habitats, and ecosystems. So that's the project aims to protect and improve the ecological and the environmental situation of the river basin. So Three Gorges Group since 2018 played essential role in this great protection project on the urban water management and environment protection. We established a mode called Urban Smart Water Steward. Basically, Three Gorges act as a steward to manage all the water issues of a city. Since 2018, we have already invested over 28.7 billion US dollars under this great protection project. It's via the public, private, and partnership. Now it's covered 55 cities along the Yangtze River. Currently, Three Gorges Group operates 660 treatment plants, mostly on the wastewater side, with a total treatment capacity of 4.5 million cubic meter per day. And we also manage over 50,000 kilometer drainage pipes. So this slide basically shows where Zhejiang City locates. It locates at the middle stream of the Yangtze River. Under our project, it covers all the drainage facility in the central area of Zhejiang City, includes 6 wastewater treatment plants, over 40 sewer pumping stations, around 1,800 kilometers of drainage pipes, 1 sludge treatment plant, and 6 regulation reservoirs. And service population is around 3 million. So, but today I only talk about the digital water transformation of the water utilities at Zhejiang associated with those water facilities. So first, I would like to introduce the framework of the smart water system we developed for the Zhejiang City. Basically, it has 5 layers. From the foundation layer, Internet of Things layer, supporting layer, and application module layers, and decision supporting layers. So from the foundation layer, it covers the cloud service, basic IT facilities, staffs, and GIS and water infrastructure and facility features. And for the Internet of Things, we have communications, monitoring systems, all kinds of different monitors. And for the supporting layer, have 3 middle platforms, include the data middle platform, business middle platform, middleware. And for the application modules, we also have the SCADA, working order management, and I will give more details in the following slides. And the up layer, most up layer is for the decision supporting. It's about emergency management, performance assessment, analysis, project planning and construction management, operation dispatching, and etc. On the right, we also see 2 important systems we have. Is one cybersecurity system. For the smart system, we put on everything online. It's very important to have a cybersecurity system in place. And we also have standard systems because we integrate great protection of young project. We have covered a large number of cities. So we developed a standard systems. We basically make sure the same standards applied to all the projects. So basically, these standards covers like data standards, operation standards, and communication standards. This and such. So in total, we have already published over 80 corporate standards for the grant protection of Yangtze River project. Yeah, these slides, I present the system interface of the system we developed based the framework I just introduced. So this from this interface, the up part you can see several buttons, maybe not very clear, but it's basically the manuals, drop-down manuals. You can have all the functions embedded for these systems. And the left side also have some buttons. They can also link to the different data, shows different data and functions. And also in the at the bottom, there's also some functions available as well. So in the following slides, I'm going more to give more slides to show the system we developed. So as I previously mentioned, we have embedded over 80 function modules within these systems. On these slides, I just give some graph to list some of the important major modules like energy network, equipment center, wastewater treatment plant management, protection work water center, mobile apps, monitoring center, and safety management and so on. So far, we opened over 300 user accounts, and not only for the water utility staff, we also opened accounts for the government parties like Water Resource Bureau, Environment Protection Bureau, and such. We also produced over 1,400 standard reports for the operation and management of the water utilities. Those reports greatly improve the efficiency of the daily management. Previously, before we developed these systems, water utilities only use the manual filling tables or form or reports for daily reporting. So it's really a big improvement for this standardized reports. And daily operation and management data records exceed around 60 or 50,000 entries per day. That's really a huge as well. As Oliver previously mentioned, now we have more and more data. So how to manage this data also is an issue for the water utilities for the digital water transformation. This is basically the monitoring system we developed, we deployed for this project. So we have video cameras, rain gauge, flow meters, water quality instruments, water levels, and remote sensing, and drone, internal manhole covers, and gateways. These kinds. We installed these instruments at rivers, outfalls, pipe networks, flood and prone location, pumping stations, water treatment and regulation reservoirs, etc. On the right, I list all the monitors we installed so far. We will continue adding more monitors. We noticed that these monitors that we installed so far is not sufficient, and when the new demand rise, we will install and install more and more monitors in the system to support our daily operation and management. This graph, the graph in the center of this slide basically gives a layout of monitors we currently have within the systems. all the green labels at one location. It's not necessary to be only one instrument. It can be several instruments or just one locations. And these photos basically is our colleagues working at the site to install the monitors and to collect data and see how the monitors can work. And so I also want to mention that this intelligent manhole cover alarm. So we have some equipment uh, installed underneath the covers. If it's unauthorized opening of these covers, it will immediately send the alarm message to the control center, and the inspection staff will be sent to the site to check what happened at the site to make sure the covers can be managed properly. Okay, this is the data management. What we have done for the data management. Basically, we collect all the data from different sources, include operation, what's assets, work process, monitoring data, and design drawings, numerical models, data records, Gs. We input this all this data in the system, and we assembling them, and we process them, and we analysis and to in order to support the further applications of water management. We also develop a 3D visualization of this data. We put the model together and the drawings and the GIS together with the overlaid with 3D and data together. So we also developed some digital tools for the whole life cycle management of PACS networks, covering the existing facilities and planning and design stage, construction stage, commissioning stage, and operating stages. So it has at each stage has different functions, and those tools will be applied at different situations. For example, the first tools were going to be used for the surveyor at the site. As I mentioned previously, we have standards systems. So all the surveyor have to follow our standards. Those tools will be a great approach to enable them to follow our standards. They have to import or submit all those survey data at the site. And once they submit, they will send to the control center, and the in-house staff will to do the checking. We also, of course, we also develop some automatic checking algorithm. But above that, we also have manual checking as well. So to check the data quality, only the data past the checking, quality checking, they will be fully imported into our database. The second tool is for the identification of the problems associated with data. Basically, we develop some algorithms to check the inspection images and videos, like CCTVs videos, to automatically identify those problems associated with the pipe facilities, such as like blockage, collapse, and like leakage of the pipe. With basically its identify location, what kind of problems the surveys needs of these problems, and also we link this data with GIS and also with model as well. The third tool is we developed the construction management tool for the water facility construction management, is the schedule, the construction process, and construction quality control as well, and also being models. Yeah. The fourth, we tools we developed is for the monitoring and systems. And finally, another tool is overall and integrated for the operation management system. Basically, all those previous tools are embedded or has connection with these operation management systems. We also have developed modeling systems embedded in these management systems. We use the simulation engine, Swim and ListFront. So because this is open source, we can we did some further development to merge these two engines together and also to via APIs to connect with the management systems. So we can trigger the simulation from the system platform. Uh, um, and we can also, after the simulation, all the results can be sent to the platform and present on the platform. So, and these models are online continuous simulations, 24 hours, 7 days per, yeah, continuous modeling. And it's also linked to the latest monitoring data and operation data. Basically, use monitoring data to update the initial condition of the next run of the models, and also the input operating data to tell the model what operation have been done. Yeah, basically, it's to make sure the model can simulate properly in a proper way to represent what happened in the systems. Continue to talk about the modeling. So we also use this model to incorporate the rainfall observations in like I present an example of the rainfall event. And we also have the radar rainfall forecasting data. So we import meteorology forecasting data into the model to do the flooding forecast or the overflows forecast for the combined systems. On the left side of this, you can see this the squares basically is cover is basically the coverage of the data for rainfall radar rainfall forecastings. And all these orange dots it will, indicating locations of rainfall gauges. So basically, we combine the observation of the rainfall and with the rainfall forecasting data. So the modeling results and observations and the video records are checked online as well to check each other to see the accuracy of this data, the model and to just make sure to understand what happened in the systems, and then based on the simulation results, and we have already developed some scenarios for the dispatching, so we can send the trucks, pumping trucks, or the staffs on the site to deal with the problems at the site to try to eliminate the problems as soon as possible. Yeah. Then based on those, we also then come back to talk about the digital twin of the drainage network. We put them all those functions embedded in systems, and we developed the digital twin systems, and also especially for the 3D representation of this energy network city. So you can see this is the manholes and the pipes, both the storm water pipes and the brown ones is the sewer pipes. Yeah, we not only work on the pipes, we also work on the treatment plants and like pumping stations, all the facilities. This is a small wastewater treatment plants fully designed constructed and operated by 3 Gorges Group. This is underground treatment plants. Its capacity is 30,000 cubic meter per day. It have 2 underground layers. On the ground, it's a public park, so it's open to the public, so everybody can come to visit this park. But underneath this park, it's a treatment plant. So we developed a digital twin system for these treatment plants. So all the facilities, all the process of these treatment plants have been incorporated into this system. So we also incorporated daily operations functions like work orders, inspections, these things, and video cameras, these things, and monitors, instance, etc. All the functions we think it's useful and available to support daily operation, we have to incorporate it into these systems. This project started in 2019 and finished in 2021. Then, as I mentioned, we not only developed a 3D visualization of this treatment plants, we also developed some other functions like intelligent aeration, and intelligent chemical dosing, and like a video cameras check if any alarm sent to the central control center. And we also developed the apps for the staffs at the wastewater treatment plant to basically they are same systems, but just the staff can work on the desktop and can work on the mobile apps as well to control the process. And so this is the central control centers we develop for these smart water systems. So it can be used for design support of the major events. And also for daily operations, the staff have several screens, basically collect all the like present all the facilities, the operation, the conditions, operation conditions at all the states of the systems. So, and also we in this another photos we can see virtual inspectors. So we are thinking in the future with use visual inspectors instead of really a real person to do the inspection works, routine inspection works. So to save the manpowers. So at this central control center, we can basically remote control all the facilities, including the wastewater treatment plants, regulation reservoirs, pumping stations, alarm queries, deal with alarm queries, and energy consumption situations, etc. Yeah. Finally, I do a summary on the achievements of this project. So it has 38 improvement in operational and 38 improvement in operational and maintenance efficiency, 26% improvement in energy efficiency, 60% reduction in the maintenance failure rates, 80% of the process operations and safety training are currently based on the digital twins application technologies. And the 6 successful cases for pollution source tracing and source pollution control. And this control center, we also use it as an educational resource for the public. So averagely, every year we receive 100 visitors to this control center from very different background of the visitors, can be government, students, and even just the general public. And more than 10 patents and over 40 software copyrights we developed based on this project. So that's all for my presentation. Thank you.
Wonderful, Yufeng, and thank you very much. We have one or two questions in the chat. If you are putting Q&A questions in, please use the Q&A box, not the chat, the webinar chat box. Otherwise, we will miss them, and in the Q&A box, they are traceable. The one question I've got in the Q&A box is, are there installed sensors in the sewer for real-time monitoring of wastewater quality? Now, based upon, I think you had pod online COD in there, so probably yes.
Yes,
Yeah.
actually, most of the monitors are real-time monitors. They are going to send back to the control center.
Is it for quality as well as flow, Yufeng, or
The quality of, for example, like COD,
yeah,
these things. Yeah.
yeah, perfect. Another one was, what algorithms did you use and what challenges were faced in training them?
Yeah, we do have, to be frank, I think the system is not perfect now, and because it covers so many different technologies, and our the database and data foundations is not perfect as well. We got a lot of data, but as we usually say, so currently we are data rich, but the quality poor. So the data quality is sometimes not sufficient to support to afford the very in-depth, sophisticated algorithms. But we are step by step, like the modeling I showed, the accuracy still keep improving. Some locations or some storm events, the predictions is not good, and the quality is. We are still try to improve the quality and efficiency of that. So the algorithms, I may I didn't understand what exactly the algorithm asked for but I may because it's a big group to work on together, so it's different people work on. I may not know all the details of this, but if I will look at these questions and answers in later stage.
Perfect, thank you, Fang. I think at that we'll move on, but if you do have any more questions, do put them in the Q&A box and the Q&A box only. Don't put them in the chat as I've just seen popped up. And we'll address them in the Q&A at the end of this next presentation. So our next presenter is Marina Macedo, the Brazilian water professional currently working as an adjunct professor at the Federal University of Ituba. As part of her responsibilities, Marina is responsible for representative of the Civil Society and Academy at the Rio Grande Watershed Committee, and is a member, of course, of the Digital Water Programme Steering Committee. She's also an associate editor of Hydrological Sciences journal. She holds a postdoctoral qualification in public and environmental health by the School of Public Health at the University of Sao Paulo, a PhD and a master's in sanitation and hydraulic engineering by the Sao Carlos School of Engineering, again at the University of Sao Paulo, and her main subject expertise is flood and water management, climate change mitigation and adaptation, and hydraulic modeling and water geopolitics. Marina, do you want to take over?
Thank you so much, Oliver. So, as Oliver already mentioned, my main expertise is in flood management and climate change. So today I will go into present a little bit about the digital water and how they can help in actually build resilience to these main extreme events that we are passing in terms of rainfall and heavy storms. So I'm going to present a little bit the general aspects of the resilience and the importance that we have in terms of this in these current days. And then later I'm going to present a case study that we have developed here in our university from the small cities that we have here in Brazil. So to start, just to have this background in terms of resilience and in terms of the importance that we have to develop these digital tools to improve the resilience to floods specifically. We have the new IPCC report, the RS6, that have different projections in terms of different increases in the median temperature of the Earth. And one important outcome that we have from this report is that even if we have only 1.5 increase in degrees Celsius increases in the global temperature, we will have an increase in terms of 1.5 in terms of the heavy storms if we are considering just a return period of 10 years. And we can see that this even increases more and more even when we have higher increases in the temperature of the globe. And unfortunately, we can see that this is the path that we are going in terms of generation of GEEs and etc. So given that 55% of the world population lives in urban environments, we need extremely urgent need to have these adaptation plans to strengthen the urban resilience of water, sanitation, and specifically this stormwater drainage infrastructure. And this is not only for one place or another, one country or another. We can see by the projections that we will have an increase in heavy precipitation in almost all of the places in the globe. And we have already feeling this since some years ago. I'm sorry that these are news that we have here in Brazil, so it's in Portuguese, but I will just translate it for you. So these are the images that we have for the floods in Germany in 2022 that have lived more than 100 people dead and 1,000 of people disappeared. Also, just remembering that huge flood that we have in Pakistan in 2022, also that have lived like 1/3 of the country underwater. We also have nowadays, like I think 1 week ago, or even still going on in Spain, these major floods that have lived a lot of dead people as well, and chaos in the country with a lot of loss in terms of infrastructure. So this is a really high topic that we have to discuss, and we have to create alternatives on how to deal with it. And just focusing now a little bit more in terms of Brazil to start going for our case study. We also have a lot of these events happening here in Brazil. So here are two examples that we have also in 2022. This first one was in the north part of Brazil, where we have a major flood that left like more than 5 cities underwater for more than 1 month in the Bahia state. And this other one was, I don't know if you have seen this in the international media, but it was a really important event that we have a compound event of heavy storms and landslides that have passed on the state of São Paulo. And we have over 200 people that have died in these landslides. And it was a really quick event, so the time for having a warning system must have been like really quick, otherwise people wouldn't have time to leave their houses, and that's exactly what happened. And specifically this year, we have like this major flood also in the state of Rio Grande do Sul that also have take place like for more than 1 month, that the entire state, mostly the entire state, have gone underwater as well. So here is a picture of the city of Lajeado, and here these like yellow spots are actually the public illumination systems that were also underwater. So these have caused like we have a raise in the water level of the river more than 30 meters. So it was a really, really important flood that we have in this region. So this is actually was just to fomentate a little bit the importance that we have in terms of creating different tools to actually deal with this flood resilience, and how these digital tools can help on the different parts of the cycle of the resilience. So in terms of the importance of this team, in the Digital Water Program, we have developed a white paper with many other people, not just me, in terms of authorship. That is the digitalization journey of urban climate resilience and case studies on flood management and resilience. In this white paper is still going to be published, I hope, until the end of the year. We have discussed a little bit the general terms of urban resilience in terms of flood, the different technologies that we have to help in the different steps on the resilience cycle. And we also have provided different case studies in terms of how these technologies are being used on different places around the world. So we have case studies from Ghana, we have case studies from Brazil, we have case studies from Spain and from Singapore as well. So I really hope that you can read this white paper later if you have more interest in knowing a little bit more about the other case studies. Today I'm going to present more about the case study that we had from Brazil, but just before that, I would just like to define better what is resilience and what are the terms that we are using here in this white paper and also in my presentation. So the United Nations Agency for Disaster Risk Reduction have defined resilience as the means and the ability of a system, community, or society exposed to hazards to resist, absorb, accommodate, and to recover from the effects of the hazard in a timely and efficient manner, including through the preservation and restoration of its essential basic structures and functions. So in general, we are looking here as the capacity of try to avoid the hazard itself, try to deal with the hazard when it happens, and also later recover all of the infrastructures and the public health and the general well-being of the system after the event happens in the most rapid way that we can. And this is like the definition that we use for resilience in general terms. But when we are talking about urban spaces, we also have some definitions about what we mean in terms of urban resilience and what we mean in terms of urban sustainability. So in terms of urban resilience, we can define this as the passive process of monitoring, facilitating, maintaining, and recovering a virtual cycle between ecosystem services and human well-being. And when we talk about urban sustainability, we talk about the active process of synergetic integration and coevolution between the subsystems making up a city without compromising the possibilities for developing of surrounding areas and contributing by this means towards reducing the harmful effects of development on the biosphere. So this is what we are aiming, these two aspects of urban resilience and urban sustainability is what we should aim when using these digital tools to improve flood resilience. So we have constructed here a resilience cycle that goes from the disaster itself happening, and then we will have this individual response for people that try to deal with these disasters when it is happening. Then later we have the response, that is actually how the community itself and all of the organizations will try to respond in a common way to the disaster that is happening in that specific moment. Then after the response, we will have the rehabilitation, that is trying to restore all of the functions of the system itself. Then we will have the reconstruction, that is the action of rebuilding all of these infrastructures that were somehow lost by the disaster. And all of these parts here, from the individual response until the reconstruction, we are talking about post-disaster, so how to recover from the disaster after it happens. After we have reconstructed our system, we have to also think about how can we deal with the disaster before it actually happened. How can we reduce the risk of the disaster itself? So here is what we call the part of the cycle that is the pre-disaster. So in this part, we will be aiming mostly on mitigation actions. So how to, if the disaster happened, what are the actions that we can have to try to decrease the impacts that this disaster will have on our system. And also, we have to think about preparedness. So we could not mitigate the disaster will happen, how we will be prepared to deal with this disaster. So this is what we call the resilience cycle. And looking at this resilience cycle, we could identify different ways on how these digital tools can actually help on these different steps of dealing with the flood resilience. So here we have all of these types here of that we have this symbol here is where we could identify possibilities to have these digital tools helping on the resilience cycle. So in terms of individual response, we could have the communication of the disaster warning to the population and civil defense in a manner that is more efficient and using these digital tools. In terms of the response, we can have the communication of the disaster response to the population. We also have these wireless sensor networks, the unmanned aerial vehicles, and also voluntary geographic information to assess the priority affected sites. So we can send specifically help to these places. And also using these UAV would be really helpful to try to support and identify evacuation routes. This is one of the problems that we have here in Brazil during the floods in Rio Grande do Sul that I've shown you before, is that people actually didn't know how to evacuate from their cities or from their places, because they usually roads that they use to go out of the city or even out of their houses in the city were actually flooded. So using these unmanned aerial vehicles would actually help a lot on identifying alternative routes. In terms of rehabilitation and reconstruction, we could have these data-driven techniques, enhancing flood insurance. We can also have this VGI and UAV coupled with the flood modeling to identify priority reconstruction sites. When we are talking about mitigation, we can have all of these digital tools to create warning systems. That this is actually one of the, I would say, the most important thing that we have to do when the disaster is happening itself. We have to warn the population, we have to somehow warn people that the disaster is going to happen, and in a time-efficient manner that people can actually respond to it. We can also use this voluntary geographic information to collect additional data, and this is actually really important in terms of cities and in terms of countries that don't actually have a lot of money to expend on digital sensors and etc. Because we need this information that come from the population and can now actually be processed in terms of valuable information to calibrate our models or even to update them in real time. This is really helpful when we are talking about ungauged basins, that is the mostly of the basins that we have here in Brazil, for example. Also, having this real-time monitoring and real-time control would actually help a lot on also improving the prediction of the systems. We also would have this modeling and risk mapping that is important for us to see which are the part of the cities or the populations that are actually being affected by the flood. We also have the possibility of using digital twins to more flexible operation of flood mitigation infrastructure. And Yufeng have already showed a really great example on how they are doing this in China. And in terms of preparedness, it's really important for us to also have these early warning systems that actually give us data updated in real time, nowcasting technologies, modeling, also these real-time monitoring and real-time control. So this is just a general idea of how these digital tools can help in these different parts of the resilience cycle. And we already have a lot of examples in the literature and even in the real application on how this can be used. So I really suggest for you to read our white paper later. And now, coming in specifically from the case study that we have in Brazil, we are presenting here a flood monitoring and warning system in urban areas based on LoRa 1, that is this long-range wide area network. And I will be presenting a case study for the city of Itajubá. That is a small city. We have like less than 100,000 people living here. And also the system is being applied in different cities around Itajubá as well, that are cities that usually have less than 50,000 people living. It's important to mention that this flood monitoring and warning system have been developed not by me, I'm just representing them here. It has been developed by this group of 4 researchers. So they have started the development of the systems in terms of academic research in my university here, the University of Itajubá. And now they have opened a company that is actually putting this new technology on the market. So it's the Aston Tecnologia. The challenge that we have addressed here in this case study is to develop a monitoring and alert system for urban areas that is based on a compact measuring stations that have low construction cost, minimal energy consumption, and simple maintenance, and also that can communicate the measured data to the user in an objective manner and also in an accessible language. So I'm going to be discussing about each one of these challenges here. So the first one is about the monitoring and alert system for urban areas. And when we are talking about creating a system to warn people about the flood disaster itself, we cannot just like have rain gauges or flow meters anywhere. Like we have to think about this strategically, because we know that different places on the city will have different hydrological responses to the rainfall and even for the flood wave. So this is a first step that this project have done, that is actually having a hydrological study of the basin to choose where are the better place and the most strategic spots. Actually have installed the rain gauges that would be able to provide the best response in terms of spatial variation of the rainfall, and also in terms of the hydrological response. So sometimes if the rainfall will fall in downstream of the basin, for example, it would not have the same effect if it was on the downstream, on the upstream of the basin, and if it was also in a place that is highly urbanized. So this is important for us. So the first step is actually to have this hydrological study of the basin to choose the better places to install this monitoring system. And also the same thing we have in terms of the flow and the depth meters, because we have to be able to catch the flood wave as it happens. And this is especially important in terms of flash floods, because we can have like the beginning of the rainfall and the beginning of the flash flood in 20 minutes. So we have to have a good monitoring and a quick response in terms of these variables that we are actually monitoring. So this was the first step of this case study. So the second step is actually creating a compact measuring station. This is important because we need to, when we are talking in terms of cities, if we have like this big hydrological and meteorological measuring stations, sometimes we don't actually have the space in the city to put them. So we have to develop as small as we can, so it can be placed on, for example, these illumination posts or even on other regions. So this was actually a great concern in terms of developing this equipment. The first models, they were actually really big, and they have been able to reduce them to be a size of, for example, a cell phone, like an developing these contact measuring stations is important in terms of the spatial availability, but also it's important to have like a discrete equipment, because we have a lot of thefts here in Brazil. Like, you know, if we have like these big equipments and people know that they are actually valuable, we would be dealing with a lot of thefts. So it's important also to have like this discrete measuring stations, so people, like, it will not be a focus for this. And also a different thing that they are doing is trying to create these advertisements and explain for the population what is actually these measurement stations and why they are important. So we can also create an education in terms of flood preparedness. The other aspect that we have faced here a lot also was the low construction cost, the minimal energy consumption, and the simple maintenance. So these were challenges. These are actually really high challenges, because the urban areas, they require different temporal scales, and usually we are talking on less than 10 minutes. Like if we could have, like, in terms of each minute would be the best option, because the hydrological response on the urban areas, they are usually in terms of 10 to 30 minutes. And this requires a lot of memory and energy consumption, and hence this leads to high costs. So this was actually a great concern in terms of how can we develop a system that have this ability to acquire a lot of data and also do not require a lot of energy in terms of that. Another challenge that we have faced here is that the flow and the depth meters, they are usually really costly, and they have, like, I don't know exactly how to say this in English, but like a closed communication. For example, if you have a sensor for a company, for example, it would only be read by a data logger that is from the same company. So this is a problem, because usually this leads to high costs in terms of the operationalizing the entire system as well. So this was a challenge that we were facing also, because a lot of these flow and depth meters that the municipality have, or even the university have, they were from these companies that are closed communication. Also, the strategic it's important to have these strategic places for the rain gauges, but sometimes this could be out of the coverage range for 3G, for example, for internet, for example. So what would be the best type of communication that would allow for these rain gauges be installed in these remote places, but also keep communicating in real time? And also the high costs of installation, operation, and maintenance are a barrier to small and medium cities to adopt these systems, because usually these small and medium cities, they have low budget for everything, and they would prioritize, for example, education, health, and other things than even sanitation, and not preparedness plans for flood mitigation. So it's important for us to have like the low cost as possible on the systems, so they can be actually be implemented by these small and medium cities that have these budget constraints. So in terms of this, the solution that was thinked by this equipe here in the university was to develop a component that have all of the data reception and transmission module via LoRaWAN, that is this long-range wide area network. Also, they have developed a system that is called Marlin, that is this one here on the side, that consists of a digital circuit board where sensors are connected and data is received and sent to LoRaWAN receivers. This is a module that is extremely compact, have really low energy consumption. It requires only a small battery. And this small battery can last for a month without needing a solar panel for recharging. So this is actually really, really good in terms of energy consumption. And also this module in the circuit board, it can be connected with no matter what sensor. So they were also able to close the proprietary protocol, as someone have mentioned here in the chat, to connect these in this circuit board. And but like even though they were able to break this proprietary protocol, one important thing is that they are preferring to use sensors that are nationally manufactured and also that are low cost. And this is an important thing in terms of flood management, because we don't usually the sensors, they are really high in costs because they have a really good precision in terms of how much they can read in terms of centimeters and etc. But in terms of flood management, we don't actually need a lot of precision. The most important thing for us is to understand the pattern of the flood wave, for example, and how if it's going to actually flood or not, how this where are the areas that is going to be affected. So using low-cost sensors, like even, for example, the ones that come from the Arduino circuit, is a really a good alternative for us here, because we can have a lot of them, understand better the pattern of the flood wave, and not necessarily have a really good precision. So this is a really important thing for when talking about flood management as well. And this system also, it's really simple to have all of the maintenance of it, and the Aston company will also provide all of the maintenance that they need. In terms of communicating the measured data, they have a board to communicate the data to the user, that it looks like this one here on the right, sorry. Also, the data visualization is graphical, and we use like color scales to indicate the alert thresholds in terms of normal, attention, and emergency. I don't know if you can see like here in this graph here, but we have like a yellow line, a red line, and a green line. And these are these threshold alerts that is built for each hydrological basin specifically. This is important because when the user is looking into the data, sometimes they don't actually know like if half meter, 1 meter, 2 meters are low or high, and this will also vary in terms of each different basin. So it's important to have a communication that is easy to understand. Like if the people look into it, they know that is what is the level of alert that they are talking about, not only the raw data in terms of the level of the river. And it's also possible to set the viewing period and the sex numerical data as well, if you don't want to see only the alert thresholds. And another important thing is that this system here, in terms of flood management, it's only accessible for the civil defense. The population don't have access to this raw data, because the civil defense have to first look into this data, see if it actually makes sense or not, see the state of the community in that moment, and then have the data communicated. This is important to do not generate panic in a situation that don't necessarily need to be panicked. So this is an important thing also in terms of communicating this data. To define these alert thresholds, we have also a lot of hydrological studies and modeling for each of the basins. Generally, it's used the HEC-HMS, and also a model that we have developed here in Brazil, that is the big basins model, this MGB here. And also we calibrate these systems according to the information of the civil defense in the location. And as the system collects data since they are implemented and they keep collecting data each time, and we have like the civil defense telling if actually it was flooded or not and where it was flooded, the system learns itself with this data. So we have like this artificial intelligence model that are trained to improve the prediction as the system collects the data itself. And after the civil defense looks into the data, they actually go and communicate the data for the population. So we have here these announcements from the Aston company with the civil defenses of each region, where people can read into it and have WhatsApp channel for the civil defense to communicate the different alerts that they have to send to the population. This is trying to be, it's still a part of the system that they are trying to improve in terms of if it would be possible to send the alert to all of the people who are actually on the cell phone area of that region. But it still is something in development. So the entire development of the system is based on several years of cooperation between these team members and the municipal civil defense teams. And this also is really important because you have to construct the system to actually help to improve the municipality deficiencies and needs that they have. And this would only be possible to build if they have this collaboration between the academia and the municipal civil defense teams. This is a tool that is still in development. It requires continuous improvement. Also, the success of it will really depend on this heavily collaboration and trust of the civil defense members and other agents involved on the system itself. And it's important that we also understand that the best technology available is that one that actually help to improve something that the municipality needs and also can overcome the barriers that the municipality have. So even though our system is really simple, it's really low cost and also can attend to the needs of the municipalities in terms of budget and the communication of the data. So from my part, that was it that I would like to present to you, and I hand over the word to Oliver again.
Thank you, Marina. If you stay on camera, because we've got a Q&A session, a bit of a short one because I think we've run over, but that's absolutely fine. Any questions, do put them in the Q&A box. Yufeng, if you want to join us back now, there are a few questions for you sitting in the Q&A box. I will run through them as far as we can go. So this one's for you, Yufeng. And the modelling approaches were data-driven based or mechanistic mostly, especially for the wastewater treatment plant?
Yeah, we based on the mechanistic model. We currently use the West++, but now we from DHI. Now we are developing our own model with the treatment process model as well. It's still mechanistic models. We use Modernica to develop the different treatment process modules and put them together, and also again embedded within our systems to let the model to run continuously by itself. Yeah.
So a bit of a follow-up question. How feasible is this model over a range of population sizes? Are there any minimum or maximum sizes that the model can go? No.
No.
Okay.
No.
Easy one.
No limits on that.
Okay.
Basically, yeah. It's I think the three model is for the network models. It can simulate for large cities, and it's already have successful applications so far.
So I'm going to put the next two questions in together. What are your perspectives for more efficiency in optimization? Do you envisage working with generative AI? And the next one after that was what kind of model you use, machine learning or biokinetic? I think you've answered that. It was mechanistic.
Yeah. Well, so far we haven't adopt generative native AI, but we start to look at it, and we discussed a lot with, especially with universities, academic staff, and we have some collaboration projects on research to how to apply generative AI to the water problem issues. But as I know, in China, we do have some early stage applications based on generative AIs in wastewater treatment plants, and also for the knowledge systems. So like for the training new staff, they put all the regulation standards, also training manuals in. So once the trainee has asked the questions, and the AI is going to give the answers. And also in another situation is the government employee when to go to the site because we got a lot of regulation requirements and standards and etc. So he basically just asks the questions. The result is like this, whether or not it's offend any standards or the regulation requirements. So the AI will give the immediately an answer and tell him that what kind of standards offended, not follow. So it's really useful. I think that's a good successful application, I think.
Definitely. If there are any questions for Marina, do put them in the Q&A boxes. I think we've just covered what the next one. Next question, is there any AI support included into the system? I think you've just mentioned that, yes. I suppose some places have seen sort of chatbot approaches for customers, certainly AI nowadays, but AI definitely, I think, has a place, but depends what you look at it. If you look at it, is it machine learning? Is it deep learning? Is it artificial neural networks? Those have been used in wastewater treatment plants for a while, and I'm sure included in the digital twin in China. But when we go into generative AI, I'm not 100% sure myself at the minute, the use of it. And I think we come up against the ethical issue of how much should we be using generative AI for? Because of course it's quite a high power consumer. And what should we be using that generative AI? It's a question. It was asked. I was in a meeting recently, and it was asked, what should we be using generative AI for? I've seen wastewater treatment plant designs by generative AI, but they're not quite there yet, to my personal opinion. So it's an interesting question. Marina, certainly for the flooding approach, I think Google have developed a flooding system which is pretty good. And I don't know how that works, particularly what sensors they're using, but somebody certainly saw, I think I saw it, they've got it accurate to a few meters. What are the other applications? What else is out there that could support on a regional stroke local basis?
So in terms of generative AI, just because we were talking about this earlier, this is actually something that we are using now to try to have a structured data collection of VGI, that is this volunteer geographic information. Because, for example, in these engaged basins, we use a lot of the VGI, and usually during flood events, we have a lot of videos and photos that are being taken of the flood event itself. And this can help us to update our models as they are running in real time. So for us, like to extract the information of these videos and these pictures and these photos, like humanly, it's kind of and in a lot of volume of that will arrive to us, it's kind of impossible. So we are developing a system using ChatGPT to extract the information of these pictures, videos, and photos in terms of water level. And this has been really helpful for us to actually calibrate and update our models with the actual information that we are having on the site. This is also important because sometimes even if we have the flow meters in the rivers, in the flood event, they are carried out away because the velocity of the water is really high. So we are using this generative AI in these terms. For the applications that we have, like the one from Google that you have commented about, this is really good in terms of these higher floods, because we can classify floods in terms of river floods and pluvial floods. So for the river floods that are more gradual in terms of times, these platforms that are global, they actually worked really fine, and this is the example for the Google one. But when we are talking about flash floods, that is more caused by pluvial floods and is in urban places, they do not actually have the capacity to have this scale of information that we need, like this small scale that we need, and in terms of the prediction of the time also, because as I said, it's like 5 minutes to 20 minutes that we need. So this is the major challenge that we still have, like in urban places, we need to have more like local systems that are able to capture this time scale and spatial scale that we need. But yeah, the one from Google is a really good one. We are still analyzing it if it really can capture all of the information that we need. And yeah, I think that's it.
Marina, is that where something I saw a number of years ago now, social media mining comes in? So social media mining, people posting photos, people posting messages on social media. I suppose putting things on social media is probably the last thing you're thinking about when a flooding's coming, but maybe.
Yes, there is a paper that we have actually cited on our white paper, that it was from a researcher here from Brazil, that he was able to do this data mining in Twitter back then, X now, and use the words that were related to rainfall to actually predict the amount of rainfall. And this was really interesting. He had a really high correlation between the number of people who were tweeting about rainfall and having this now testing of the rainfall for the flood events, these flash flood events. So this is actually a really good thing for us to think about.
And a last question before Erin gets me to move on. Marina, is the Aston system considered for a spin out for commercializing?
Yes. They start doing this, and they already have like 4 cities that have buy the system. I don't know how to say.
Brilliant. Fantastic. But at that, I know Erin's got more slides for me to go through as a bit of a wrap up. Thank you, Erin. There are some upcoming IWA webinars and events. There's 3 webinars coming up. One on the 18th of November, on climate change and coastal development in Kuwait. One on the 4th of December, water security, governance, economic development and finance. And one which I presume is in Spanish, as it's coming up, as it's in Spanish there, on seguridad hídrica, gobernanza, desarrollo económico y finanzas. Of course, next week is the Digital Water Summit. I hope to see at least some of you there. If you're there, do say hello. I think Erin's got a video for me. So thank you, Erin. That is next week, so do come and join us there if you can. Also, the IWA webinars 24 at 20% discount off new membership. So if you're not already an IWA member, do use the discount code there. And hopefully hope to see you on a future webinar. So thank you very much for joining today. The recording, as I've noticed in people asking in the chat, will be shared on the IWA Connect website as well as the IWA website. So hope you've enjoyed today, and look forward to seeing on another webinar soon. Thank you very much for Yufeng and Marina for presenting. So thank you all.